Okay, so we had left off at this geometric compatibility in the last class, and just to revise again, I mean we were supposed to find the deflection of this point D. Okay, and revise the objective of the problem. Now we have arrived at this, and now we want to study the relationship between force and deformation in line with the steps 2.1. So let's see how we can do that. So for the bar BD, okay, for the bar BD, you would want to write that delta BD is equal to root 2 of x. This is the force, okay, and now you want to divide this by the area ABD. Okay, what would be the modulus? That would be E, and the original length was root 2 L. Okay, so this is just like the Hooke's law, which you had the force upon area by delta upon original length, and this was equal to the modulus of elasticity. So this is for BD, and you can root 2 into root 2 gets multiplied, so you get 2 XL by ABD E. Okay, now this is also the statement of a Hooke's law for uniaxial loading. Now for CD, delta CD, what is the force which you have? That is X. So this is for compression, okay, this part CD, and that is why it is acting only in this axis. Okay, the bending deflection will come in this direction. Okay, so delta CD is equal to XL by E ACD. So this is due to compression. Okay, this is due to tension, and we had already found out which of these bars were in tension, which of these bars were in compression earlier in the chapter 1 and 2. Okay, now finally we want to write the vertical deflection of the cantilever beam CD. So look at so if you look at table 8.1, and this is a case of a beam which is having this end load P, okay, and that value is 10 to 20 kilonewtons. So now you are not taking the compression into it, because that you have separately taken. So that would give you a value of delta V, that is equal to P minus X into L cube by 3EI. Okay, so X is basically anywhere, so delta V as a function of X. So here we have made the assumption that the bending of the beam is unaffected by the compressive load. Okay, this is not completely true, as we shall see in the next chapter. Okay, in the chapter on buckling, we will see that the bending and the compression are not unrelated, but we shall proceed on the basis of this assumption, and then after obtaining a solution we can reconsider this question, just like we are reconsidering this horizontal force now, this one, and which we did not consider in the earlier example. So we will again reconsider this assumption that the bending of the beam is unaffected by the compressive load when we learn about buckling in the next chapter. Okay, so we take these equations which we have just found out, and then we can add them into the compatibility equation over here. So delta V, so put delta BD here, delta CD into here, okay, and then delta V over here, right? So you will then be able to write this value. So that would be x. I think this is a capital X. Okay, so where did it go? This is a capital X, I guess. Okay, so this, so because this delta V is at point D, so it's not at any X, it is at X equal to L. Okay, so this is put in, then you get a relationship between X is equal to P divided by 1 plus okay. So once you put in the numbers which you have a value of P, you know the areas, you know what the second polar moment would be for the area of the cross section, and you know the value of L. So X can be found out to be 19.60 kilonewton. Okay, and then you put the value of X into this delta V and delta H, you should be able to find. So delta H is nothing but delta CD. Okay, over here. So you will be able to get delta V is equal to 0.090 m and delta H is equal to 1.76 mm. Okay, I think now we have enough information for us to be able to make certain comparisons. So comparisons with the earlier values. So we shall estimate first the error in our assumption that the compression in CD did not affect bending. Okay, let's take that um, first. So in figure 8.16, we have a free body diagram of CD and it is shown with loads X and P minus X. So let's see. And then X in this direction, and then you have X vertically. Okay, so this value will be equal to P minus X because there is a P, there is a X in the opposite direction, and similarly you have a P minus X over here. Okay, so this will keep this in equilibrium, these forces, and they are coming from B directly. I mean this diagram is not new. Okay, and then the MC is already given. Okay, so you want to free body diagram CD showing with the loads X and minus Px with the deflection delta V, which we were obtained in the above analysis. So delta V is already shown, that value we have found, X we have found out, P minus X is known. Okay, now to obtain a rough order of magnitude check on this, just like we did for the maximum tensile, so we did it for the maximum shear stress, I'm sorry, in bending divided by the maximum normal stress in the axial direction. So MC due to compressive load divided by MC due to transverse load. Okay, so let's see the compressive load first. That would be 19.6 versus this is the lever arm. Okay, so that would be 19.60 kilonewton into 1.76 mm divided by MC due to the bending moment. So the moment about C due to the transverse loading, that would be P minus X, which is this 0.40 kilonewton multiplied by the length 3 meters. So this would be 3, and if you want to write it in mm, that would be 10 to the power of 3 millimeters. So this ratio comes out to be 0.029. Okay, so this ratio indicates that any additional bending in CD because of the compressive load would only be of the order of 3% of that due to the transverse force. So this ratio is roughly around 3%. And since we assume that all the bending was due to the transverse force, our solution for the transverse force P minus X may be in error by about 3%. This would, however, make very little difference in the value of X or in the deflections G. So thus we conclude that the effect of compressive load on bending can be safely neglected in this case. Okay, so this sort of validates or verifies our assumption because it's only contributing to 3%. The ratio is only 3%. Now let's see what is the, so we had already also taken an assumption about clamping at C. The bolts were clamped at C. So let's study that assumption and see what is the possible error in this case. Okay, so compared to example 1.3 and 2.4, where we had assumed a pin joint at C, in this case we have assumed a clamp at C, and we first compare the deflections directly with the results of example 2.4. Okay, so if you want to find G, okay, so this particular values which you have, so this is G, and you want to compare this with the result of example 2.4. So let's go to example 2.4. Okay, and in this example we had in 2.4, example 2.4, we had found out that delta H was equal to 0.0915 mm and delta V is equal to 1.77 mm. Okay, and this is what you have got in the present analysis. So it is safe to say that the difference is less than 1%. I mean, you can compare the error, and so in the clamped case it is lesser. So this is the clamped case, the deflections are lesser compared to the pinned case. Okay, if we next compare the wall reactions, we find at B there has been a 2% decrease in the tensile force. Okay, so let's see where you can calculate. So in 2.4 itself I am assuming, please turn to example 2.4. Okay, so in 2.4 the reaction at B, at B it was 28.3 kilonewton, and at C it was 20 kilonewtons. Okay, So there was so at B there has been a 2% decrease. So 28.3 is what we have over here, and in this case, what do we have? We have root 2 times of x, right? So root 2 times of 19.60 is very close to this value, and that is what they say, that at B there has been a 2% decrease in the tensile force. At C the situation is more complicated. So at C you have 20 kilonewtons horizontally in the pinned case, okay, in 2.4 example, okay, but in the clamped case a vertical component and a clamping moment in addition to the horizontal component is there, okay. So figure 8.17a shows these separate components. So in the clamp case you have a 19.60 kilonewton force, okay, which is x you have calculated 19.60, so that is shown, and then you have this moment at C, that is 120 kilonewton meters, and then there is a vertical force which is P minus x, that is 40.40 kilonewtons. And what do you have in from the pin case? So in pin you only have a 20 kilonewtons force over here. So this is how it looks for clamp. This one force is how it looks like in pin, okay. So if you convert this to an equivalent force system, you will be able to get something like this: 19.60 kilonewton force acting at a point C dash, not at C but C dash, and this is C dash is separated from by C by this value, and this angle is 1.17. First thing is verify this. In your APL 100 you have learned a way how to draw an equivalent force system or a moment system, so please see how you can come from this to this, okay. And that is something without doing which you should not move ahead on this course, because it will not matter. And if you recall, we had done a similar thing in when we assumed friction in the pin. So we had some forces, and then we had seen that there was actually an offset like this by a certain distance d. Okay, so the offset distance CC dash is obtained from the requirement that the moment about C should be the same in figure 8.17 A and B, okay. So you will have this offset between C and C dash. So if we compare the single force in 8.17 B with a 20 kilonewton force acting horizontally at C, we can see the differences between the two cases, okay. So what are you comparing now? You are comparing this with this. So what is the difference in magnitude? The difference is magnitude is not much. There is 19.60 and 20 kilonewtons on one side. So this difference is about 2%, okay. Now what is the, so it's the line of action that has tipped through a small angle. So this is the small angle of 1.17 degrees through which this force is acting, and this is a small compared, the point of application has been shifted to a distance which is small compared with the distance BC. So if you look at the distance BC over here, so this offset of CC dash 61.2 mm is not much, because the length of BC is around 3 meters. So you have, is it 3 or okay, yeah, so 3 meters and 61.2 mm, I mean the ratio is very small. So that is what they say. It is shifted through a distance which is small compared to the distance BC between wall reactions. Why are you comparing with the distance BC? Because the CD dash has shifted vertically downwards. So it is reasonable to compare it with BC, which was the original length. So as a result of the comparisons made above, we should be led to the conclusion that the precise nature of the connecting joints in a structure made up of a slender elements loaded only at the joints has very little influence on the deflections of the structure or on the external reaction. So this is a very important conclusion, and you look at the effort which we have taken to arrive at this conclusion. I mean, we had already done the first part in chapter 1 itself. Okay, and after doing all this we found that the answer was more or less the same, but the very fact that now we know this gives us greater confidence when you try to idealize any problem. Okay, so as a result of the comparisons made above, we would be led to the conclusion that the precise nature of connecting joints, okay, either a pin or a clamp or a bolt in a structure made up of a slender element loaded only at the joints has very little influence on the deflections of the structure or on the external reactions. Okay, so we have seen that this is in fact the case. As a result, the designer is justified in basing his or her calculations of these quantities on the simplest model of joint behavior. And what is the simplest model of joint behavior? A frictionless pin joint. Remember, we started with the friction pin joint as well, but then we figured out that the difference between frictionless and with friction pin joint was not much. Then we compared it to the clamp one, okay, and then we found it was the assumption of frictionless pin joint taken right away in the first chapter that was the easiest to deal with, and it would give you an answer which is very close to the other answers. Okay, so one can say, well, I mean, it seems all of it is lost and we are not we are not getting anything new. Well, you have gained new knowledge, you have applied new concepts, and yet you have found in this particular problem that your very first assumption was fair enough. You couldn't have said it then. That makes all the difference. You couldn't have said it at that point. So now you know about this. Okay, so although the choice of joint idealization has led to little changes in the displacement and reactions, it would be wrong to say that there has been no significant change. Okay, there has been some change, and we have not yet considered the stresses in the individual members. So the member BD, okay, this member, the member BD is in uniaxial tension in both cases, has had only a 2% change in stress. The member CD, however, is in uniaxial compression in the first case and in combined compression and bending in the second case. So CD in the pin joint was under this loading, but in this case it is definitely under this condition, and there is also a bending. Okay, this The member CD, however, is in uniaxial compression in the first case and in combined compression and bending in the second case. The combined stress would be greatest in the bottom flange of the beam. You know this, right? Because of this bending, the bottom flange would have the maximum stress. Okay, the combined stress. I mean, the one due to compression is the same. Okay, but in this particular beam, the combined stress will be maximum over here because the bending part will be maximum. The bend stress due to bending will be maximum near the flange. Okay, bottom flange. And since it's in compression, the bottom flange is what we are considering. Okay, where the direct compressive stress and compressive stress due to bending are additive and would have its maximum value at C. So you would have its maximum value at C, the bottom part of it, at this particular point, and this peak stress in CD in the clamped case, this particular point is the maximum, having the maximum combined stress, and the value of this maximum peak stress can be calculated. So what you do is just calculate the stress due to the compressive one, then add the MBY by I ZZ. Okay, so that you will do, and that this value would be 15.12 mn by meter square. Okay, and if you had only the compressive one, like in the pin one, you would get this value of 6.25 mn by meter square. This type of a joint restraint can cause significant local changes in stress distribution even though the overall effects are same. So one point to note, if this thing has to fail, most probably it fails at this particular point. But the chances of failure, I mean, how do you as a designer decide? You always see the maximum stress over here and then perhaps compare it with some criteria. So in this particular case, the clamp one, you get that value as 15, and in the pin joint one, you get this value as 6.25. So this value is more than twice different, and hence we are saying that it's not like we didn't find new insights. Yes, the structural behavior etc. were not very different in this particular problem, but we have found some very interesting new insights into the maximum stress. Therefore, thus the type of joint restraint, either a pin or a clamp, can cause significant local changes in the state. It's local change because it is about 1 point, even though the overall effects are small. So a wide variety of structures like buildings, bridges are assembled from slender members. If the joints are pinned, the structure is called a truss. If the joints are rigid, the structure is called a frame. Okay, these are two separate words. If the joint between slender members is pinned, it is called a truss. If it is rigid, if the joints are rigid, then it is called a frame. Okay. The members of a truss carry axial load while the members of a frame generally carry shear forces and bending moments as well as the axial load. So there is a difference between truss and frame, and you should be aware of this definition right away. The structure which we have just analyzed, is a simple example of a mixed structure because it has the joints B and D are pinned as in truss, but the joint C is rigid as in frame. So it's a mixed structure. The procedure followed in analyzing the simple structure can be extended to structures with many members and many combinations of joint restraints. Although the process is straightforward, the amount of calculation required for a complex structure, I mean, think of a structure, say, of the Howrah Bridge, which we had seen earlier in the course. Okay, you want to apply these arguments which we have learned throughout this course. even though they are easy, but it will take a lot of time. So then you have some structural analysis softwares for this, and your textbook gives a small code about how you can do that in that program. It's called STRUDL, STRUDL. Okay, fine. So that's where we sort of get this part out, and the forces and the moments acting on each member are given with respect to a local coordinate system for that member in that program. Okay, that is a very common thing to do in any computational tool, that the all the forces and moments are localized, and that would be like if you have this as your element, one member, so the coordinate system will always be fixed like this: axial force, shear force, bending moment. So you're out of those thousands of structural members in a bridge or a building, you will have a value of all of them like this for this orientation it through that software. Okay, so if you are into structural engineering, means many of your colleagues in civil engineering uh, perhaps will do some courses in structural engineering or structural mechanics later on. So this is what they use for the computational part of it. Okay, having said that, let's move to section 8.5. Okay, and let's see what this section tells us. So it's a load deflection differential equation. I mean, so we have done this several times, right? From chapter 3 we have been doing it. First we do it according to 2.1, and then what we do, we take a differential element. So we have done this for axial loading, we have done it for twisting, we have done it for bending, and let's do it for the deflection as well due to bending. So we have found the stresses due to bending, let's see the deflection due to bending. So as an alternate to using the moment curvature equation 8.4 to solve the beam deflection problems, we can make use of an equation which so it starts by dv by dx plus q. So this is something which we had seen in chapter 3. Okay, and this is dmv by dx plus v is equal to 0. We can express the bending moment in terms of the load by eliminating v. So you eliminate v, what you do is you put this over here, and you would get d2mb by dx square equal to q. Okay, so this is like 3.11 and 3.12, but you can check the numbers exactly. So you would get 8.5 after this. Okay, so q is the loading, okay, per unit length. And if we now combine 8.4 and 8.5, so this is 8.5, and if I just check back what 8.4 was, 8.4 was ei d2v by dx square is equal to mb. This was 8.4. So you want to combine 8.4 and 5, you get a single differential equation relating the transverse load intensity function q to the transverse deflection v. So that would be d2 dx square ei d2v dx square equal to q. So the transverse load intensity and the transverse deflection are related by this equation, which is 8.6. Okay, so one of the observations which you can see is that ei, which is the flexural rigidity, has been left inside the parenthesis. Okay, what this means is that in the most general form, this particular equation will apply to beams where EI is not constant throughout the beam. Okay, so this equation, because you see this, the origin of this equation is the equilibrium equation. Okay, and so equilibrium is valid irrespective of whether E varies with x or it remains constant with x. So that is why we have, in the most general form, we have taken this over. Of course, if it is constant, you can always pull it out. There's no problem with that. One of the other things is, to arrive at this equation, we have used equilibrium equations, and you have used both the equilibrium equations and the deformation equations to arrive at this equation. Okay, so can you figure out the deformation relation which has been used? I mean, clearly you have this over here. Okay, and this is coming from 8.4, and 8.4 is coming from a relationship between the curvature in MB and the deflection in MB. So you have taken both of them, equilibrium equations and deformation relations. So the boundary conditions, what are the boundary conditions in 8.6? That will include both the equilibrium conditions and the geometric compatibility conditions, and that the geometric compatibility normally has, for example, the deflection at this particular point is 0. Okay, that's one of the examples. The slope of it can be 0, and for the equilibrium conditions, the equilibrium condition will have restrictions on the shear and bending moment at certain points. For example, you may have a bending moment over here, you may have a shear here or not. Okay, so those are some kind of boundary conditions. So we would want to write the moment curvature equation, and for that you can say, look at equation 8.4. so the shear force V, how can you write the shear force V over there? Okay, so this is shear force V. So what you do is, V would be equal to minus of d by dx of mb, and mb is ei d2v by dx square. So please note, there is a small v and there is a capital V. This is the capital V, this is the small v. This is the deflection, this is the shear force. Now if you look at figure 8.19 to 8.22, let me see if I can pull all of them. Yes, figure 8.19 to figure 8.22, we show appropriate boundary conditions. So if this is the equation, I'll just write it over here. V is equal to okay, so 8.19 to 8.22, the boundary conditions are shown. So let's see what they are. In this particular case, the deflection is 0 and the slope is 0 over here. Okay, at this particular point, which is x equal to 0. And in this particular case, okay, you can have essentially a free movement in the horizontal direction, but no, there is no constraint on the rotation. There is no constraint in the, so there is, sorry, there is no constraint in the horizontal direction, but there is definitely constraint on the rotation and on the horizontal vertical movement. So you have the deflection and the bending moment, which is 0 over here. In this particular case, there is no constraint in the vertical motion, so you would have the shear force is 0. Okay, and the slope is clearly 0, and you can have an horizontal force which will not be equal to 0 in this case, the reaction at the ends. And similarly, when you have a free end, this is the free end which you have. So free end would, just like it is free, okay, just like the end of a cantilever beam, if you are not applying a load at the end, so it will not have a moment at its end, it will not have a shear force at its end. Okay, so that's how it is. One of the things is, I mean, just be very careful about these boundary conditions and understand and convince yourself whether they are actually, you are fine with them. If you are not, please discuss with me why do you think that you should not have a boundary condition like this, because these are all coming from your APL 100, so it doesn't seem there should be a problem, but if there is, please don't let it linger, please clarify from me. Okay, so that's where we are, 8.22. So we have this comment before this, which tells us that in order to solve a beam deflection using 8.6, the equation 8.6, okay, this is 8.6, d2 by dx square ei d2 v by dx square equal to q. So to be able to solve your beam deflection problems using 8.6, it is necessary to obtain an expression for the loading intensity. Definitely you will need this, which is valid over the length of the beam. Okay, and we can use the singularity functions which we have used before, just because their integration is very easy and perhaps very well known. And for most standard loadings, like a point loading, point moment, or a concentrated loading, concentrated or a ramp sort of force, everything has a singularity function, the integrations of which are very easy, so we can do that. Then integration of 8.4 requires 4 constants. You can see that, right? To find v as a function of x, you will need to integrate it 4 times, and hence you would have each a constant of indefinite integration every time, so you would need 4 boundary conditions. Okay, and this can be applied for both statically determinate and indeterminate, and let's see how that can be done in a problem. Okay, so you have okay, so what we'll do is we'll solve the problem in the next class, just because the time is not enough, and perhaps in the next class we can do that. There is one more thing which I should just tell you. Since it's not mentioned in this book, but it's very commonly known. Remember, you had a beam of, say, pure bending, so MB was there and shear stress was not there. Then you had the general bending, so MB was a function of x, okay, this where it was constant, and then V was not zero, okay, it was present. And in one case, obviously, you had the plane sections would remain plane, and in here the plane sections would deform, and there was a quantification in terms of strains what that deformation would be. This beam is called Euler, this is how it's pronounced, Euler Bernoulli beam, and this is called a Timoshenko beam. This is something which you should know. The reason you should know is because the rest of the world uses this. So it will be very embarrassing despite knowing everything about the pure bending and the general bending, and perhaps actually perhaps more than what most people would know, because of the way you have learnt about this subject by the reasonings and arguments and contradictions and symmetries and so on. It would be embarrassing not to know the names which everyone uses. So this is called a Timoshenko beam, perhaps after the people who had given the original ideas, and this is called the Euler-Bernoulli beam. So the pure bending is the Euler-Bernoulli beam, and the general bending in which the plane surface may not remain plane is the Timoshenko beam. So with this we end our class, and in the next class we will continue with the example 8.9, and then we will study the energy methods, which is section 8.6. Okay, and with that we would end this particular chapter, which is the deflections due to bending. Thank you.